In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about multibody dynamics module in quantum multiphysics simulation software. Today I want to go through hinge joint theory. The hinge joint, also known as revolute joint, has one rotational degree of freedom between the two components. The two components are free to rotate relative to each other about the axis of the joint. The following is an addition to the prismatic joint theory, some of which is also applicable for the hinge joint axis and its local coordinate system. In two dimensions, the initial joint axis E10, E20, and E30 are always global spatial axes with the initial joint axis E10 being the out of plane axis. Hinge joint formulation. For a hinge joint, the destination attachment is free to rotate relative to the source attachment about the joint axis. The relative rotation about the joint axis theta is the degree of freedom that formulates this kind of connection. The motion of the destination attachment is prescribed in terms of the motion of the source attachment with the following relations. The relative quaternion in the global spatial coordinate system is defined as r is equal to cosinus theta divided by 2, br is equal to sinus theta divided by 2 multiplied by e1 in two dimensions. The motion of the destination attachment is prescribed in terms of the motion of the source attachment by these formulations. Phi destination is equal to phi source plus theta. Also, UC destination is equal to UC source. Joint elasticity in each joint, the elastic degree of freedom, are written as blue. Now I want to go through the cylindrical joint theory. The cylindrical joint theory has a one rotational and translational and one rotational degree of freedom between the two connected components. The components are free to solid and rotate relative to each other along the axis of joint. The cylindrical joint can be thought of as a combination of a prismatic joint and a hinge joint. The following is an addition to the prismatic joint theory and hinge joint theory, which are also applicable for the cylindrical joint. Cylindrical joint formulation. For a cylindrical joint, the essential attachment is free to translate and rotate relative to the source attachment along the axis of joint. Thus, the degree of freedom in this joint are the relative displacement u along the joint axis and the relative rotation theta about the joint axis. To formulate this kind of connection, the motion of the destination attachment is prescribed in terms of the motion of the source attachment as B destination is equal to B prime. You see the description destination is equal to UC source UR. The relative quaternion and the relative displacement vector UR in a global spatial coordinate system are defined as follow. For example, IR is equal to cosinus theta divided by 2, BR is equal to sinus theta divided by 2 multiplied by E1, UR is equal to UE1. Joint elasticity in cylindrical joint, the elastic degrees of freedom are written as follow. So the next theory would be a screw joint theory. The screw joint is similar to the cylindrical joint except that the relative displacement and relative rotation, instead of being independent, are linearly related to each other. Hence, this joint effectively has only one degree of freedom. The following is an addition to the cylindrical joint theory, which is also applicable for the screw joint. The screw joint formulation. For the screw joint, an extra constraint is added to enforce the relation between the relative displacement and the relative rotation theta. U is equal to m multiplied by p multiplied by theta divided by 2p. Here n and p are the number of stars and the pitch of the screw thread, respectively. The next theory would be planar joint theory. The planar joint theory has two translational and rotational degrees of freedom between the two components. Both components are free to translate relative to each other in a plane perpendicular to the axis of joint, and they are also free to rotate about this axis. The following is an addition to the cylindrical joint theory, which is also applicable to the planar joint. Planar joint formulation: for a planar joint, the destination boundaries are free to transfer relative to the source boundaries in a plane perpendicular to the joint axis and free to rotate relative to the source boundaries about this axis. The degrees of freedom are two relative displacement along the second and third axis of the joint, U2 and U3, and one relative rotation about the joint axis, which is theta. The joint formulation is similar to cylindrical joint. The only difference is in the destination of the relative displacement vector. Joint elasticity: in planar joint, the elastic degrees of freedom are written as follow. Ball joint theory: the ball joint, also known as a spherical joint, and the three rotational degrees of freedom between the two attached components. The two components are free to rotate relative to each other along all three axes. The following is an addition to the hinge joint theory, some of which is also applicable to the ball joint. Ball joint axis and its local coordinate system. Unlike other joints, the ball joint has no particular axis about which the relative degrees of freedom between the two components are possible. This joint has rotational symmetry and hence relative rotation is allowed about any axis. However, application of constraint, springs, dampers, and so forth needs a source E1 and destination ED. One axis, the local coordinate system of this joint, is defined using the source axis. You specify the initial source axis E10 and initial destination axis E destination 10 in terms of components. Along the axis of the selected coordinate system, the initial source axis must point toward the center of joint, whereas the initial destination axis must point away from the center of joint. The process of creating a rotated source axis, rotated destination axis, and a corresponding local coordinate system is the same as for the hinge joint. The auxiliary axis is taken as the initial destination axis unless it is parallel to the initial source axis. Now I want to go through the ball joint formulation. For ball joint, destination attachment is free to rotate relative to the source attachment about all three axes. The added degrees of freedom are contained in a relative quaternion A, B, C, and D, which represents the rotation in three dimensions. The rest of the formulation is similar to that of the hinge joint. Joint elasticity in ball joint is only translations are constrained in a ball joint. The elastic degrees of freedom are such as this formulation. Therefore, there are only elastic forces and no elastic moments or coupling matrices, such as follow. The total elastic joint forces can be written using the springs and damping forces as follow. The contribution to the virtual work is as follow. Sludge joint theory. The sludge joint has three rotational and one translational degrees of freedom between the two attached components. The components are free to rotate relative to each other about all three axes and also free to transfer along the joint and translation axis. The slot joint can be seen as a combination of the prismatic joint and the ball joint. The following is an addition to the prismatic joint theory and the ball joint theory, which are also applicable to the slot joint. Slot joint axis and its local coordinate system. For a slot joint, the translation motion is free along the joint translational axis, which can be either the source axis or the destination axis. Translational degree of freedom is added along the joint translational axis. You can specify the initial joint translational axis each translational zero to be either as follow. For the slot joint, The process of defining the source axis, destination axis, and local coordinate system is the same as for the ball joint. The joint coordinate system is always attached to the source part even if the joint translational axis is defined by the destination axis. A slot joint formulation. The slot joint formulation is similar to the ball joint except that an external translation degrees of freedom is needed. The joint translational axis is used for the relative displacement vector and the rotational degrees of freedom are represented by a relative quaternion as in the ball joint. Joint elasticity in a slot joint. The elastic degree of freedom depends on whether the joint translational axis is defined to be the source axis or the destination axis. In both cases, there are two constraint translations, but it is only when the source axis is the joint translational axis that the elastic displacement can be expressed in the joint coordinate system directions such as follow. When the joint translational axis is the destination axis, then we have this formulation where E destination 2 and E destination 3 are second and third axis of the destination coordinate system respectively. In this case, the stiffness and damping matrices are given along the destination axis when the joint coordinate system is selected. Except for this difference, the formulation is the same as for the ball joint. Now I want to go through the reduced slot joint theory. The reduced slot joint has one rotational and one translation degree of freedom between the two attached components. So both components of the system are free to rotate about the joint rotational axis and free to translate along the joint translation axis. The reduced slot joint can be thought of as a combination of the prismatic joint and the hinge joint with different axes for the allowed degrees of freedom. The translational axis and the rotational axis are orthogonal to each other. The reduced slot joint in two dimensions is similar to reduced slot joint in three dimensions. The only difference is the initial joint rotational axis irrotational 0, which doesn't change in two dimensions and it is always out of the plane axis E0. The following is an addition to the cylindrical joint theory, which is also applicable for the reduced slot joint axis and its local coordinate system. The translation motion for a reduced slot joint is free along the joint translational axis, which can either be attached on the source attachment or the destination attachment. The translational degree of freedom is added along the joint translational axis. In addition to the translational axis, information about the joint rotational axis is also required to specify its components in the selected coordinate system. In this joint, the initial joint axis E10 and initial second axis E10 and 20 are the same as the initial joint translational axis E translational 0 and initial joint rotational axis E rotational 0 respectively. If these axes are not orthogonal on input, then the rotational axis is adjusted in the plane spanned by E translational 0 and E rotational 0 so as to fulfill the criteria. Reduces slot joint formulation. The joint formulation is similar to the cylindrical joint except that the translation degree of freedom is defined along the joint translation axis and the rotation degree of freedom is defined about the joint rotational axis. Joint elasticity reduces slot joint. The elastic degrees of freedom are written as follows. Clearance joint theory. The clearance joint allows two points that are connected to a pair of attachment or rigid domains to move within a specified clearance distance. The components connected to a clearance joint are free to rotate relative to each other about all three axes and free to translate relative to each other within the specified clearance limit. The following is an addition to the ball joint theory and the hinge joint theory, some of which is also applicable for the clearance joint. Clearance joint formulation. In three dimensions, the formulation of the clearance joint is similar to a ball joint except for the translation constraints. Analogies. In two dimensions, the clearance joint formulation is similar to a hinge joint. Instead of translation constraints, a penalty-based formulation is used to enforce that the distance between specified points on both selected components is between the clearance distance. The penalty force is computed as follows, where FAG is a joint force magnitude and PAJ is a penalty factor input having a default value of 0.1 multiplied by diagonal multiplied by E equality. In this expression, E equality is an effective Young's modulus and diagonal is a geometric diagonal of the bounding box of the geometry. The gap variable is difference between the clearance and the distance between the connection points D. The distance between the connection points D is calculated such as follow. Here is a sourcing to destination or the unformed locations of the two connections points, and U source and U destination are the corresponding displacement. Fixed joint theory. The fixed joint rigidly connects the two components and doesn't allow any relative motion between them. It doesn't add any degrees of freedom. The following is an addition to the prismatic joint theory, some of which is applicable for the fixed joint. Thank you so much for watching my tutorial video until the end. Today is the 7th day of the May 2026. Time is 8:54 o'clock in the morning. Also, you can download the prepared and proper simulation file from my github.com/masterscript.